On paper, the IBT-2 H Bridge module looks very attractive. Plenty of amps, simple control interface and a very attractive price make it look like the ideal component to build a powerful DCC booster. But then there are numerous reports from people running into problems when using the device, particularly when it comes to current sensing. Time to find out why that is and what can be done about it. Welcome to the IoTT channel. I am Hans Tanner. For my tests, I used two different IBT-2 modules, both available on Amazon for little money. The first is what probably can be called the standard IBT-2 module, as this is the one you get pointed to first when doing a Google search. It is based on the BTS7960 chips for a maximum current of 43 amps. It is the module that many of us know from the DIY booster design David Botner did a few years ago, which I reviewed in video number 34. The second module I tested is a similar one, but without the dominant cooling block. The description on Amazon is slightly misleading as it references both the BTS7960 as well as the BTN7970 chips as H Bridge chips for the board. Well, when I ordered the modules, I hoped they would come with the BTN7970, as the BTS7960 is no longer produced, but the devices I received had the BTS7960 chip installed. And if you order these boards, make sure to inspect them before use. From the two modules I ordered, one had the controller chip misaligned by one pin. I placed a customer complaint and received a replacement board. When I tested them, only one of the boards was working, the other was dead. I then touched all the driver and controller chip pins with a soldering iron and that did the trick. Apparently a soldering problem, but it suggests that these modules were never factory tested, so be careful before using them. To get started, let's have a look at the schematics of the IBT-2 module and identify the differences between the various versions that are available. Compared to the motor shield board used in videos number 103 and 104, the IBT-2 module is a completely different device. The L298 on the motor shield is a single chip that has two full H bridges on it, so 2 times 4 transistors to control 2 output channels, and the entire control logic is integrated on the same chip as well. The IBT-2 module supports only one channel and has 2 individual half-bridge chips with 2 transistors each and therefore uses an extra driver chip to control the transistors, and each half-bridge can be switched on and off individually. For our DCC application, this means we need to provide a positive and a negative copy of the DCC signal compared to only one input on the L298. The second big difference to the motor shield is how current sensing works. On the motor shield, the full output current is fed through a small resistor and the voltage drop on the resistor is proportional to the current flow. Of course, with a maximum output current of over 40 amps on the IBT-2, this is no longer possible. Instead, the BTS7960 chip features a current source that outputs a current that is proportional to the main current going through the chip. This current is then fed through a resistor, and as before, the resulting voltage drop is proportional to the current from the current source and therefore to the current through the H bridge. However, there are differences between the chip types and the sensing resistors used on the various boards. The first difference is the current divider implemented on the two different chip types. The BTS7960 has a divider of 8500, meaning that 1 mA coming out of the sense pin IS stands for 8.5 amps current through the H bridge. The newer BTN7970 is using a higher divider of 19500 and 1 mA on the sense pin means an H bridge current flow of 19.5 amps. The other difference is the current sense resistor used on the various boards. The standard boards with the aluminum cooler and BTS7960 chips normally use 10K sense resistors. However, the board without cooler that I am testing here features 1K sense resistors, which means the resulting sense voltage for the same current flow is only 1/10 of that of the standard module. BTN7970 equipped boards also seem to have 1K sense resistors. At least that is what is shown in the schematics that are available on the internet. With these numbers in mind, we can easily generate the current to sense voltage curves shown here. Knowing the curve is important because the analog input of the Arduino is limited to 5 volt maximum. The BTS7960 using a 10K sense resistor is therefore a potential risk, as it will output 1.17 volts per amp and therefore reaches 5 volts analog voltage at a bridge current of 4.27 volts. With that in mind, we can now connect the control pins of the IBT-2 to the Arduino. 5 volt and ground are a no-brainer. They are just connected to 5 volt and ground of the Arduino. The enable pins are also easy to do. We can combine them together as we don't need to shut down the half bridges individually and connect them to the I/O pin of the Arduino that is set up as power pin in the motor driver setup. For the PWM pins we have two options. We can use 2 pins on the Arduino set up in the motor driver settings as signal pin and signal pin 2 and connect left and right PWM individually. Or we can save an output pin on the Arduino and connect one of the pins to the signal pin output and then use an inverter chip to connect the second PWM pin and generate the negative copy of the DCC signal. I like to be conservative on the Arduino pin usage, so that is my preferred solution. Finally, for the sense pins, the DCC signal triggers the H bridges alternatively, only one at a time, so we can combine the sense outputs together and connect them to the Arduino analog pin defined as current pin in the motor driver setup. However, we should be aware what we are doing here. Looking at the schematics, we see that when combining the 2 sense pins together, we really connect the 2 sense resistors in parallel, which means the resulting sense resistor, and therefore the analog voltage, is cut in half for the same output current. Which means that even if the board is equipped with 10K resistors and BTS7960 chips, the resulting analog voltage for a current of 5 amps is only 2.94 volts, which is greatly reducing the risk of overloading the analog input of the Arduino, and using a Zener diode as extra protection is probably not necessary in most cases. And with that, the IBT-2 module is connected to DCC EX. The power connections on the other end of the board are straightforward. Connect a power supply to the inputs and the track to the motor output. On the standard IBT-2, the inputs are labeled B+ and B- and the outputs are M+ and M-. On my other board, the inputs are labeled VS and ground, and out 1 and out 2 is used for the track output. In any case, make sure not to reverse the polarity because the modules are not protected against that. After powering up DCC EX and connecting the power supply to the IBT-2 module, we are ready to do some testing. First, I check the track voltage under no load conditions, and I am particularly interested in the polarity change, so the moment when one half bridge shuts down and the other is powering up. And I like what I see, it is as expected. Even when zooming in to 20 microseconds per division, the flanges are steep and pretty symmetric. When loaded with 5 amps, the signal still looks good and symmetrical. The voltage is lower because it is reduced by the power supply to limit the current to 5 amps. Also, the short spike at the end of the DCC half bit is due to the voltage regulation of the power supply. It just shoots up a little in the moment the current is shutting down. So that is pretty good. It looks like the IBT-2 makes for a cheap, powerful and high quality output booster. Now let's look into current measuring, and that is where the scary stuff begins. First, I connected an ohmic load of about 500 milliamps and hooked up the two channels of the oscilloscope to the IS pins individually. This is what I got for the two IBT-2s. In both cases, there is a significant difference of the returned analog voltage between the two channels. In the case of the standard IBT-2 with the 10K resistors, one channel reported 3 times higher current than the other. The no-cooler IBT-2 showed a difference of about 25%, better than the standard module but still not suitable for current measurement. I repeated the measurements for several current levels up to 5 amps, and here are the results for the standard IBT-2. As we see, the difference between the two channels is the biggest for small currents. The larger the current gets, the closer together are the results, and near 5 amps they are almost the same. Looking at the no-cooler IBT-2, we see the same, even though that module performs better, but still not good enough for the measurement of small currents. Next, I placed a locomotive on the track. As in the last videos, I used one with a low PWM frequency Digitrax DH84 decoder and one with a 16 kHz decoder with back EMF from Method. And as discussed before, I combined the two current sense outputs into one input for the Arduino, shown in red, and added the DCC pulses in blue. Here is what I measured on the analog input of the Arduino, first with speed settings at 10% and then 50% of maximum speed. In both cases we can easily see the difference of the measured values depending on what channel of the IBT-2 is active. With such a difference between the two sides of the DCC signal, a meaningful current measurement as discussed in video number 104 is basically impossible. And while thinking about what I saw in these curves, it dawned on me that this difference of analog voltage between the two sensor outputs is probably the very reason why there are so many people reporting difficulties when trying to use the IBT-2 for service mode programming. To understand that, we need to have a quick look into the DCC EX code sequence that detects the acknowledge pulse from the decoder. As you probably know, the ACK pulse is a brief current pulse of 5 to 7 milliseconds, which is about 100 DCC bits, that signals the programmer that a certain byte or bit value has been found. The DCC EX function that detects this pulse is found in DCC waveform and is called check ACK. It is called from the DCC interrupt, so basically twice per bit. If a current is detected that is higher than the ACK threshold, it is identified as leading edge of the pulse and a counter is started. The counter is now increased every time the function is called and the current flow is still detected. If the current flow is gone, a trailing edge is detected and the counter is indicating the length of the pulse. If it was longer than a certain minimum pulse length, typically about 3 milliseconds, it is interpreted as ACK pulse and reported. Otherwise, the pulse is discarded and the function looks for a new leading edge. With the significant difference between the measured values from each channel of the IBT-2, so from 1/2 bit to the other, this logic will fail. What happens is that the function detects a current and starts the counting. Unfortunately, already the very next half bit, which is measured by the other channel, does not report a current that is higher than the threshold value, and the pulse is discarded. As a result, no ACK pulse is ever detected and reading out a decoder CV value will fail. To fix this problem, all we need to do is adding a small capacitor between the sense input and ground. I am currently using 10 nanofarads which on a standard module with 10K resistors results in a time constant of about 50 microseconds, just long enough to support the voltage level during 1 bit so that it does not sink below the pulse threshold level. The difference is day and night, as can be seen on this screenshot. Both pictures show a series of egg pulses. Note the scaling is 10 milliseconds per division, so the pulses are about 7 milliseconds long. In the left picture we see the pulses without capacitor, including the ripple that comes from the two different channels and disturb the egg pulse detection function of DCC EX. After adding the capacitor to the analog input of the Arduino, the signal that is seen by DCC EX looks much smoother and the egg pulse detection works much more reliable. There is still improvement potential, as we will see in a minute, but the core problem, the huge difference between the measurements from the two channels, is fixed. The solution is easy to implement and it is also safe in terms of short-circuit detection, as the resulting current is always the one from the channel that reports a higher value. For the no-cooler IBT-2 with 1K sense resistors, the capacitor value should be around 100 nanofarads for a 50 microsecond time constant. All in all, the value of the capacitor is not that critical, and it seems a time constant of 50 microseconds is sufficient to prevent the measured value to sink below the threshold value of the pulse detection. This simple measure increases the success rate of decoder readouts to probably about 90% of the cases. And it also takes care of the current measurement, so measuring the current of an IBT-2 using the Red Hat current display as shown in video number 104 is comparable to reading the current from a motor shield. But there is one situation remaining that still can cause problems, and that is if there is an overlap between the no-load noise of the IBT-2 and the threshold value of the egg pulse. Apparently, the noise level of different IBT-2 modules is not always the same. On these screenshots, we see the noise of the standard IBT-2 compared to the noise of the no-cooler IBT-2. The standard IBT-2 noise peak-to-peak value is maybe about 30 millivolts, while the noise of the no-cooler device is more like 50 millivolts peak-to-peak. This is really strange, as the standard IBT-2 has a 10 times higher sense resistor, so one would expect to see a higher noise level. It looks like the quality of the chips is just better than that of the chips used on the no-cooler device. Or maybe the current source regulation works more precise on a 10K load than on a 1K load. I don't know the reason, but we have to be prepared for some noisy analog signals. The other problem is that because of the lower sense resistors of the no-cooler IBT-2, the distance between the peak values of the ground noise and the threshold value of the pulse detection can come very close to each other. And if they even overlap, ground noise peaks may trigger a leading edge detection and reading of a CV value will fail. Now, the DCC EX software is basically trying to calibrate the leading edge detection. Here is how it works. It reads the value of the current feedback and then calculates the required egg pulse current by adding the additional pulse current of 50 milliamps as set in the DCC EX code. This works well as long as there is not much noise and the measured value is the same every time. But in the case of my no-cooler IBT-2 with the noisy sense output, the measured value is somewhat random between the positive and negative peak value. As a result, the calculated threshold value for the pulse detection is changing with every new CV readout command, and if the threshold is based on a very low measured value, it may very well be lower than the highest peaks of the base noise. I wanted to find out if this really is the case and made a few changes to the calibration function. Instead of reading the current value only once, I ran the measurements in a loop and recorded the lowest and highest values. I then calculate the threshold for the leading edge detection based on the highest measured value, which limits the range in which the threshold value can fluctuate. I then activated the diagnostics messages and added an output for the measured minimum and maximum values of the base noise. I then ran a few CV read commands to see the effects. Here are some screenshots of the monitor output and the pulse signal. The first one is a readout of CV8 on the standard IBT-2 with 10K sense resistors and 10 nanofarad capacitor. With the small baseline noise, min and max values are both at 1 and the calculated threshold is 3. That was very consistent for every readout I did, and each time the calibration function worked and read the CV values reliably on different voltage levels. I changed the track voltage in several steps from 9 volts to 20 volts and each readout was successful. Just to verify, I then removed the capacitor and the readouts started to fail, and this was also the case for every voltage level. Next, I replaced the standard IBT-2 with the no-cooler version and repeated the test sequence. Here are again some results. Interesting to see that the calibration function now returned different values for min and max measurements. And with minimums around 1 or 2 and maximums from 6 to 8, the values differ quite significantly. Now, with a pulse threshold value of 3 added to the baseline, it can easily be seen why the readout is messed up if the calibration comes back with a low value. In that case, the calculated threshold is lower than the highest peaks of the noise. Therefore, the signal noise may trigger the leading edge detector. I verified that by selecting the minimum value as basis for the threshold calculation, and all CV read operations failed. On the other hand, my maximum value detection based on about 30 measurements seems to do the trick reliably. So I would recommend adding this to the DCC EX code base. It does not hurt too much if the baseline is stable, but helps to make the readout function more reliable in case there is significant noise, as it is the case with my no-cooler IBT-2. So let's summarize. In order to make the IBT-2 working as powerful output device for DCC EX, 2 additional measures are needed. Add a small capacitor to the analog input to compensate for voltage differences between the 2 IS pins of the IBT-2 module. And modify the setAC baseline function in DCC EX to detect the highest value of the baseline before calculating the threshold value for AC pulse detection. Okay, so with that figured out, what's next? Well, 2 things. First, I am going to make a few changes to the current measurement setup of the IoTT stick, mainly adding the possibility to configure an offset to adjust the zero level of the display in case of baseline noise. And second, I am working on a carrier board for the no-cooler IBT-2 in the Arduino Shield form factor that will make this IBT-2 board a single-channel Arduino power shield. If you are interested in that, make sure you subscribe to the IoTT channel and hit the bell icon so that you are in a premium seat when new videos become available. And that's it for this video. I hope this information was useful or at least interesting for you, and you are now able to integrate the IBT-2 module into your DCC EX configuration, including service mode programming. If so, please click the like button below to let me know. Doing so makes me happy and keeps me motivated, and it also helps to promote this video and the IoTT channel in general to other model railroaders. Thanks for watching and see you in the next video.